This is Unit 7, Physical Behavior of Matter, Lesson 5, Kinetic Molecular Theory, Ideal versus real gases. How do ideal gases behave compared to real gases? The objectives of this lesson are I can compare the entropy of solids, liquids, and gases, and I can differentiate between ideal and real gases. So do now. Entropy is defined as the amount of disorder or randomness. So entropy increases when temperature increases, when something dissolves or becomes aqueous, and it's highest in gases. So a quick review of solids, liquids, and gases again, because that's what we're talking about, the physical behavior of matter. So how the states of matter are different. In solids, we've got particle arrangement are close and ordered, they vibrate, intermolecular forces are high, they have a definite shape, a definite volume, and the entropy is low. In liquids, the particle arrangement is less ordered, they flow around each other, the intermolecular forces of attraction are medium, they take the shape of the container and they have a definite volume, and they have a medium amount of entropy. And then in particle arrangement in gases are very far apart, they're disordered, they're very random. The intermolecular forces of attraction are low, they take the shape of the container and that fills the container, and the entropy is high. So gases are most affected by changes in temperature, pressure, and volume compared to solids and liquids. So the next few lessons we're going to be discussing how gases behave. So stop and think, which state of matter has the highest amount of entropy? The kinetic molecular theory, or KMT, describes how ideal gases behave compared to real gases. So what this means is we as scientists, in order to study gases, came up with a set of rules to describe what gases would behave like if they were most ideal. So you need to understand what those conditions are. So ideal gases are imaginary; they're not real. We just make up these things, and that means that they will follow the gas laws. So our next unit lesson will talk about the gas laws. In order to be an ideal gas, the particles are not attracted to each other. The particles have no volume, or we say it's negligible, and they move in a straight line motion. And the energy, they have elastic collisions. So that means all energy is conserved. So this is what it means if we were ideal, what it would look like. In reality, real gases are what we really work with. They do not follow the gas laws exactly because they have some attraction for each other, because they have intermolecular forces. They have some volume, so think about the sizes of the different atoms, and they do not necessarily move in straight lines. They can kind of bend around corners. And when they hit each other, energy is not completely conserved. Some is always lost. So in real life, gases are real. They do these things, but when we study them and we want to describe how gases work, we make them ideal. We put some conditions on them. So if we had a real gas, it would behave most ideally under these conditions if we had very high temperature and low pressure, because the particles are moving very fast and the particles are very far apart. So this allows less chance of um, particles attracting each other. And the way that I remember this is what conditions of year have high temperatures and low pressure. That's the summer. Summertime, it's hot. There's no school, so it's low pressure. You don't have to do a lot. So summer is when gases behave most ideally. When they deviate or stray from ideal is when we have a low temperature, when it's cold out and high pressure. So this is when we're more real. Particles are moving slower and the particles are closer together. So when we're in school, gas particles will attract each other and behave more like real gases. So ideal gases are described as perfect gases, but they have some assumptions. So we assume they have no mass, we assume they have no volume, and we assume they have no attractive forces. When will real gases behave as ideal gases? When they are spread out, when the temperature is high, and the pressure is low. Another acronym to remember when real gases behave as ideal gases is plate. So when the pressure is low, ideal gases, and high temperature. I find this more confusing than summer. Summer is much easier, temperature is high, pressure is low, is when I have an ideal gas, is the ideal time of year. Gas pressure is defined as the force exerted on a container walls by particles in a gas. The units we use are the kilopascals and the atmosphere. So recall back to table A, our STP, or standard temperature and pressure. These are the values of our standard pressure. So practice. Under which conditions of temperature and pressure would helium behave most like an ideal gas? So remember, the ideal time of year is summer. So that means we're going to have high temperature and low pressure. So we're going to look for the lowest pressure. So between these two, 600 is higher pressure. And then between these two, we're going to look for the highest temperature. So here we've got high temperature, low pressure. An assumption of the kinetic theory of gases is that the particles of gas have little attraction for each other and a significant volume. Now recall that when we're making these assumptions, they have no volume. They have little attraction for each other and an insignificant volume. So those are both conditions that are true because they have little attraction, therefore we'll eliminate those two. All right, I just did it that way. So check your understanding. So now you can compare the entropy of solids, liquids, and gases, and you can differentiate between ideal and real gases.